Hi everyone, welcome to Deep Learning Talks. Today we are going to discuss the first learnable model in the whole machine learning domain, which is the linear regression. As the name suggests, we're going to predict something which is a regressive output, a continuous output that might range from negative infinity to positive infinity. And it's not discrete. So if it was discrete, we would say that it's going to predict whether the data point belongs to class A or data point belongs to class B or class C or class 1 or class 2 or class 3. So it's going to have a continuous output. It's not discrete. This is the first distinction. The second thing is the name linear. Linear means that the whole model equation is going to be linear. The highest degree of polynomial is going to be 1. So the model itself will assume that everything is linear and will produce a linear output. So before linear regression, what all did we do? I think before linear regression, we were mostly doing heuristic based qualitative intuition. For example, more the size of the house, more is the price, right? So we were trying to deduce some sort of correlation based on our intuition, based on the nature of the universe, based on the nature of the domain. And we did not have strict formulas or strict algorithm to predict the best fitted line. We also had deterministic formulas. For example, the Newton's law, right? So there were some deterministic formulas that helped us compute a few things, but we did not have a process or an algorithm to predict the best fitted line on a given set of data points, right? So what is the intuitive mental model to understand linear regression? Now that we want to move from qualitative intuition based on correlation, that more price means more the size of the house, we want to move from that intuition to a linear model, to a way to describe the best fitted line on a given data points. So what is the intuitive mental model to describe linear regression? So think of it, think of some data points as an example. For example, let's say when x is equal to 2, y is also equal to 2. When x is equal to 4, let's say y is equal to 8. When x is 5, y is 11. When x is 100, y is, let's say, 296, right? So here what we are trying to do, we are trying to describe the input, which is x. Input is mostly denoted by x. For all the standard algorithms that we read in any book or in any research paper, we always denote x as the input and y as the truth or the output. So when we put y hat, we generally mean the predicted y, or y pred means the algorithm predicted this y. When we treat y as y, then it's mostly the given truth. So here y is a given truth and x acts as a variable, as a feature, as an input feature to the algorithm, right? So we are given some data points. If we try to plot these points x and y on a two-dimensional graph, we would realize that there is some relationship in the points. So the points either increase or decrease on the given graph. So we want to be able to describe that graph. We want to plot a line. So if we did not have linear regression, we would have taken a ruler and maybe drawn a straight line, right? So by just visually building an opinion on it without any mathematical function. But now we know that we can describe the line using y is equal to mx plus c, where y we assume is the output, x is the input, m and c are the parameters, are the coefficients or the weights or the variables that describe the line, right? So m and c are the slope and intercept respectively that describe the whole line. Y is our output, x is our input. I think this is super sorted. The only objective here is to minimize the loss such that we get the best fitted line. So here we have to quantify the error. Once we quantify the error, we will be able to come up with the loss. So think of it like you produce a line that does not best describe your data. Now you want to adjust the line to a point that best describes your data, that best fits your data. This is what we ideally want to do. So we want to quantify the predictions or the error. How far are we deviated from true and pred? So what is the difference between our y true and y pred? How far are we deviated? We want a quantitative measure to compute this particular metric. We call this metric as error. Let's assume that we have y true, which is the given y, and y pred, which is the predicted y. And if we want to just compute the difference, if we compute the difference and square it, that is one way to describe or quantify the error. So this is what we do. We come up with an error function, a loss function, or a cost function, where we describe or quantify the cost. Here the cost, quantifying the cost gets very simple. For every data point, you simply do y true minus y pred. So let's say you predicted 296, whereas the truth for that particular input data point was 300. Here, your cost is 4. So you square 4, right? Because you can have positive magnitude of the cost and negative magnitude of the cost. So you square it, right? And at the end, when you square and you do a summation over all the data points, you get a large loss function or the larger loss for the whole data set. So the only intuition behind the linear regression model and computing the best M's and C is we want to come up with a way where we get the best M and the best C. What do I mean by best M and best C? The best M and the best C would be such where the loss that we quantified is minimum. If I can come up and figure out a process, an iterative algorithm that can help me come up with the best M, which is the slope, and the best C, which is the intercept, in such a way that my loss is minimum. What is the loss? The loss here is the sum of squared residual. How did we define residual? Residual is y true minus y pred. True minus predicted and the whole and doing the whole square and then doing summation to compute the loss over all data points, right? We want to decrease this loss as we go down our algorithm iteratively, and we want to adjust the m's and c's slightly. So for example, let's say this is the best fit line, but here we want to adjust our m's and c's so that it comes to the optimal horizontal, right? And how will we do that? We will do it using an algorithm known as gradient descent, right? So here, if we try to understand the mental model behind linear regression, we have something known as the equation of a line. Y is equal to mx plus c. We have two parameters, m's and c's, right? We have a cost function, sum of squared residuals, and we have an algorithm that will adjust m's and c's or find the optimal m's and c's such that the loss is minimized, right? So this is the mental model to look at linear regression. And at the end, what do we get? After the algorithm ends, after the iterative process ends, and we get the best M and the best C, we already have X. When we plug and play values, X, M, and C, which is Y is equal to MX plus C, we get the best Y, right? So the best fitted line helps us produce the best predicted Y, right? How would we use it? For example, now you give me some size of the house and you want me to predict the house prices. I can use it to build a model to predict house prices. I can use it to build any sort of a model where we want to predict some continuous value, some continuous variable, right? Now, we only have a one-dimensional x. We've only talked about one-dimensional x. What if there are two variables? For example, what if you give me super area and carpet area of a house and you ask me to predict the price? So what I'll do in that case is I will extrapolate my equation from y equals to mx plus c, and I will make it y is equal to m1x1 plus m2x2 plus c. If you give me three variables, I will extrapolate it to three variables, m1x1 plus m2x2 plus m3x3 plus c, right? So think of it, if you want to correlate it with neural network, think of it like W transpose X plus B, right? So W is the weight, M is the weight, and C is the bias, right? So you can correlate it with that particular neural network equation. Now we can have K such parameters if we have k such features. So if you give me k features, I can have k parameters, or rather k plus 1, because I will have m1 x1 plus m2 x2 plus m3 x3 so on till mk xk plus c, right? So k plus 1 parameters, k features, k plus 1 parameters, and all of this is the whole equation is going to be linear, right? This is not polynomial regression, this is linear regression, right? Now we have seen all the pieces, all the subcomponents of linear regression. The only thing that we have to do is figure out the iterative algorithm that we talked about. How do we find the best M and the best C such that it produces the best fit line, right? We know an equation of a line, that's fine. We know that M and C are parameters, that is also fine. We have a way to quantify the cost or the loss, which is the sum of squared residuals, where we have defined residual as y true minus y predicted and square, right? We could also do a modulus or an absolute value, but I think both of them have their own advantages and disadvantages. So we have everything now. What is it that we want to do, or we want to understand? We want to understand what is that iterative algorithm that helps us produce the best M and the best C. That algorithm generally is known as gradient descent, right? So what does it suggest? It suggests start with random values of M and C, right? Because we don't really know what the line feels like. We don't have a visual opinion on the line, right? We cannot visually plot MNC or predict MNC. We have not seen. The data might have key variables and millions of data points, right? So there is no concept of visual analysis, right? We want a rational, deterministic process that works for all sets of data, right? That works for all n number of data points and k number of features, right? So take random m and c. Now, if you only have one m and one c, you initialize a random value of m and c, or let's say we initialize them as 1, right? Now, the main thing is we have to plug and play values, and we once we plot the line with random MNC, we would realize that we are at a very bad fit, right? Or there's a very random probability that we might not be towards the best fitted line, right? We would generally be very far from what a true fitted line would look like. Now, what we want to do is we want to adjust the MNC such a way that the loss gets minimized. So what we'll do in the algorithm iteratively, let's say we want to run it for 1000 iterations. At every iteration, we will calculate the partial derivative of what? Of the loss function, of the cost function. Let's assume the cost function is j. J has how many parameters? M and C, right? What would j look like? J would look like y true minus y pred. Y pred is nothing but mx plus c. So we would differentiate this j function with respect to m, and we would differentiate this j function. We would take a partial derivative with respect to c, with respect to m and with respect to c. Now we have gotten two derivatives. We will update our m's and update our c inside the algorithm, inside the iterations. And how would we update? So we would simply update the old value of m is equal to, the new value of m is equal to old value minus some learning rate, right? Multiplied by the derivative with respect to m. Same for c. The new value of c is equal to the old value of c minus learning rate multiplied by the derivative of the cost function with respect to c, right? So we would keep on doing this iteratively, and we would reach our global minima where the loss function is minimized, and at every step we are trying to reach our global minima with respect to loss function, and at every step we are also trying to change or adjust the values of m's and c's so that we reach that appropriate m and c where the loss function is minimized. So this whole intuition or this whole algorithm is known as gradient descent. So what is the intuition behind gradient descent? So the intuition behind gradient descent says that let's imagine that you're standing on the top of the mountain at the mountain peak, and you see a valley down there. You want to reach the bottom, and you want to reach the bottom step by step. And at the bottom of the valley, right? So imagine it as a U. At the bottom of the valley is your global minima. You want to reach that point, right? That is the main intuition behind gradient descent. We are trying to, slope down towards our global minima, and there lies our optimal M and optimal C, which will describe our best fitted line. So this is the large intuition of gradient descent. It's basically giving us a framework to figure out the best parameters for any model. And what does the framework says? The framework simply says whatever loss function you have, whatever cost function you have, you differentiate it with respect to parameter 1, you differentiate it with respect to parameter 2, parameter 3, parameter 4, so on till parameter k, and keep on updating those parameters in order to reach your global minima for that particular function. Now, if you were learning linear regression, where should you start? So you should start by understanding the equation of the line, and then moving ahead by describing the cost function, understand how different cost functions look like, figure out the sum of squared residuals, the intuition behind sum of squared residuals, the mean squared error, the mean absolute error, and see how gradient descent views these cost functions and figures out the best fitted line. Try to visualize how a random line with random MNC tries to iteratively figure out the best optimal position with respect to its data, right? It's very easily plottable when the data is two-dimensional, and it's also nicely plottable when the data is three-dimensional. So if we have only one feature, like when x is one-dimensional, y is one-dimensional, we can produce a best fitted line. If we have two features, x1, x2, and y, we can fit a plane. If we have three features, x1, x2, x3, and y, we can fit a three-dimensional hyperplane. If we have four features, x1, x2, x3, x4, we can fit a four-dimensional hyperplane. If we have k features, we can fit a k-dimensional hyperplane, right? So linear regression does not only talks about line, it talks about fitting a linear hyperplane also, right? You can extrapolate it from a line to a plane to a n-dimensional hyperplane. So the main disadvantage of linear regression is that it assumes everything as linear. It assumes that there are linear relationships between the whole data, and it tries to reciprocate the same in the model, right? But generally the data is non-linear. The data might not always be linear, right? It cannot produce a non-linear curve. It cannot produce a quadratic, a parabolic curve. This is the this is one of the disadvantages. Now the other disadvantage is it also fails in case of outliers. It does not behave very well with outliers. Now, one interesting use case that is coming to my mind when we talk about linear regression is that linear regression is highly interpretable, right? We can kind of interpret the results that it is producing. It is heavily used in quant finance to understand relationships, not generally to predict the price of a stock, but to understand relationship. Let's say you want to understand the relationship with the stock price, let's say Google, and with respect to S&P 500. So in these kind of use cases, linear regression helps quantitative finance produce, great results. So now we have something, we have some algorithm that gives us a framework to think about all other algorithms in machine learning, because this algorithm teaches us gradient descent. This algorithm teaches us the linear model. This algorithm teaches us the idea of a cost function. And all of these three things are very standard in all the classical machine learning, domain. Now, it also gives us a need for logistic regression or solving a classification problem. We know we don't have nonlinearity. We don't have the ability in our model to exhibit nonlinearity in our data, right? We know the output is, unbounded. The output can range from negative infinity to positive infinity. It is continuous. If I can add and fuse in nonlinearity in my model, that can explain the nonlinearity in data. Along with that, if I can make my model behave as if it produces probabilities, right? Not negative infinity to positive infinity. I can get a framework to come up for a model that can do classification, which is logistic regression. So we would see, we would observe when we read logistic regression that this linear model is topped up or encapsulated under sigmoid. Along with that, this particular linear model aims to behave as a classification model by topping it up with sigmoid and by changing the cost function. That's it for linear regression. Thank you.